Today, what we're going to be talking is spectrophotometry. This is going to be found in a lot of chemical engineering and biological engineering applications. So, question here. Beta carotene, which is the orange color found in carrots, absorbs what color of light if a sample of algae are green? What color light would you want to use to see how well it absorbs light? What do you need to worry about in the design of a spectrometer? If you can add anything to this video. What do you need to do to calibrate a spectrometer? These are going to be questions that we're going to talk about. So before we start, we need to talk about the light. So light is what we call the electromagnetic spectrum, and it comes in different things. There's the visible light, which has the colors of the rainbow. And there's also the colors that we can't see but are still light. So ultraviolet light, infrared light, microwave light, radar, radio light, X-ray light. There are different variations of those lights. Anything that we see is part of the visible light, and those colors are found in it. Now, the way that they differ from each other is their wavelengths. Depending on if they have a bigger wavelength, they're closer to the red side. If they're shorter wavelengths, they're closer to the blue-purple side. So when light gets passed through a prism, the wavelengths get scattered, and the tighter, the smaller the wavelength, the purples, are going to be diffracted or bent more down, and while the larger ones are going to be refracted less so. So the reds are going to be up here, and you get your purples, and this is how you can get a rainbow. But how do we see color? Well, we have in our eyes, we have little cells where our cells can see different colors based on lights. So from a computer screen, we have three little lights. You can think of them as really, really small. There are pixels, but they have three colors, red, green, and blue, and if the red and blue are on 100%, then those come and hit our eyes, and we see a specific color. That would be magenta. Now, on the other hand, if it's a painting that we're looking at, white light hits the surface, and it bounces off the material. Now, the dyes that make up that can absorb some of those lights, such as, like, say, green light, and only allow, let's say, the red and blue to come in, and we see like a purplish hue around the sun. On the other hand, if it's transmitted, it's going to allow white light to go through it, and some of the light gets absorbed, such as, like, say, the green, and only the blue light is allowed to get through, and then we can see this different colors. Now, different molecules have different colors. So beta carotene is orange, Indian yellow is yellow, malachite green is brown. I know that's kind of a goofy one, but it is what it is. Crystal violet is violet. Red lead is actually red. There's the phthalo blue and chlorophyll A, which is what we're going to be dealing with, is chlorophyll, which is this molecule. Now, different molecules absorb different materials based off of their wavelengths. So beta carotene absorbs in this frequency, not in this. So these are the colors beta carotene absorbs, while malachite green does these colors. And so if you notice that the blue is almost non-present, that means any blue light that goes through is then able to continue on through, and that's why we see this as a blue chemical. Same thing on this side. This is why we see it as orange, because the orange makes it all the way through, while the beta carotene absorbs the purple, blues, and greens. So what is spectrometry? Spectrometry is the ability to take light at a specific wavelength, put it through something, and we get light out. Now, if you have nothing in there, it comes in through no sample, and it comes out and basically looks identical. But if you put a light source in and you have your sample, the light out can be different. And what changes is how much. By how much does it change? And that can tell us about our sample. So it can actually be a little bit lower. So the three basic components of a spectrometer is your light source, typically usually with some form of an LED that has a really good adjustable peak, so we can change that how high that is. Then you have your area, your stage, your sample stage. This is where our sample's at, and this usually will position so that the light will pass through it. So it's usually like some clear little thing called a cuvette. It's a little tiny square bottle, and the light's able to go through it. And then you have some sensor that is able to pick up the sensitivity of all of that area, and it's able to sense the differences of that chemical. And so what we can do is, if all of a sudden the sensor senses a difference, we can say that it absorbed a certain color of light. Now, in the circuit, we have this. This is our LEDs. They're going to be 4 prongs. Now, take your hand and put it up. Take your hand and put it up, straight up, like your fingers are pointing straight up. Now, the middle finger, the longest one, is our ground. Okay, and then it goes RGB. Red for your pointer finger, ring finger is green, and your pinky is blue. So you always remember that your ground is always going to be your longest middle finger, and then it goes RGB. And so you can see this one, it's kind of backwards. If you were to put your hand up to the screen with your palm facing the screen, red, ground, RGB, green and blue. And then what you can do is you can actually add in a circuit with a sample, and we have a photoresistor that measures the resistance over here. We can actually sample and get a photometer that can measure how much light is being absorbed. So we're going to design your own photometer. So what is important? Well, position and stability of that light, so that light can't be moving around. What color of light do we need? The position and stability of your sensors, and ability to not let any stray light in. We also need to know the positioning of your sample needs to be stable. So what we're going to do is we're going to measure resistance, but we need to know the concentration. So how do we get that? Well, we do a calibration set. So what we do is we take a known sample with different concentrations. So we have 100% concentration, dilute it a little bit, all the way until we have no concentration. Then we put it in. What we're going to do is we're going to use it for algae. So we're going to look at algae, and we're going to look at the concentration of algae, and then we're going to see what happens as it gets concentrated. So here is our little photometer. At zero transmission, at zero where it's blocked off, it's 100% black. So we'll take a cuvette and basically line it with black tape, and you'll see what happens when it's zero. And then what happens when the cuvette is 100% open and is not, and it completely lets all light through, and we'll see what that is. This will let us know what the transmission and the resistance. The transmission is equal to the fraction of light that is let through. Now, defining the zero transmission, we call that the resistance reading R naught, or R sub zero, and that's just basically a blacked out cuvette. And this should correspond to zero transmission in our sample, but you won't get zero resistance because there could be a noise in our circuits, some added voltage somewhere. So now finding 100% transmission, we just put it in with nothing in it, and we will call that resistance 1, R sub 1. And that's just clear water, and the resistance should correspond to 100% transmission through our sample. So then what we can do is we can then calibrate it. We write all our known concentrations in our calibration sample here, and our measured resistances over there. Once we do that, we'll have a nice curve, and we can plot that. Once we plot that, then we can actually set and find an equation and of that line, and it should be a linear line, and then we can actually plot in our sample, put it in, and we can actually get a nice sample, and we can actually know our concentrations. So we'll have you guys actually be building this, and we'll have you guys build a photoresistor and then grow some algae and test its concentration.